And in this third lecture, we'll continue with the longitudinal equations and how can we solve it. We will see the solution in this lecture. Okay, so this is what we have. We were talking about the stick fixed stability because for the stick fixed stability, the right-hand side is being narrow. And this is easier for us for our solution. And so these three equations will be reduced to this quadratic equation about lambda. And can you recall how can we get this quadratic equation? So this is by letting the determinant, coefficient matrix, determinant of the coefficient matrix being narrow. Okay, and we know for the longitudinal stability, there are two distinctive modes. One is called the short period pitching oscillation, SPPO. The other is the phugoid mode. And for SPPO, we know it has two large complex roots. And for phugoid mode, it has two small complex roots. Why complex roots? Because these two modes are oscillatory modes. So that's why the solution, the roots are complex. Okay, so let's see how can we solve it. And since we know there are two modes, we can separate the quadratic equation into two quadratic equations. And the first one is about the SPPO. The second is about the phugoid mode. And the task now is to determine B prime, C prime, K1, and K2. Okay, so this is what we have, how we split the quadratic equation into two quadratic equations. Okay, and now what we do is to find a B prime, C prime, K1, K2. The way to do it is we expand the right hand side and compare the coefficient with the left hand side, and eventually we'll have B prime plus K1 equals B, and the rest I'm not reading it. So we are at here. And now, because normally by practice we know B prime, C prime is far larger than K1, K2. This is based on the nature or property of the short period pitching oscillation in phugoid mode. And in this way, we can first solve the B prime, C prime, K1, K2 through some iterative procedure, because the expressions are not explicit. So first of all, if we look at the first equation, B prime plus K1 equals B, and we know B prime is far larger than K1, so B prime is roughly B. And the same for the next equation, C prime is roughly C, because K2 is far larger than B prime, C prime. And B prime times K1 is also becomes a very small number. So B prime K1 plus K2 is far smaller than C prime. That's why we can eliminate that two parts. And for K1, apparently we have DC minus BE divided by C squared, and K2 is roughly E divided by C. Okay, so this is the first estimation, and then we need to plug in number into the above equations to have an updated result. So we call it first iteration, and we have B prime, that's the result from the first iteration, equals B minus K1. And the K1 we use the result from the estimation. And C prime equals C minus B prime K1 minus K2. And now the B prime is updated, and the K2 is E divided by C prime, and the K1 is, I'm not reading this equation, D minus K2 times B prime divided by C. So this is updated result, and we can follow this formula, and we can use the result from the first iteration to carry out for the second iteration, and then eventually we'll see the convergence of the data, updated values. Okay, so usually we just do one iteration for some demonstration purpose. Okay, so now we know how to find B prime, C prime, K1, K2. Okay, so we know we assume the solution is in the form is a constant times e to the power minus lambda t. And since we have the quadratic equation and their coefficients, we can solve for lambda. And then the lambda should be in the form of lambda equals mu plus minus I omega. Okay, so if we know mu and omega, and we can get the time to half amplitude or double amplitude. Half amplitude is for damped mode, and double amplitude is for undamped mode. And then we can get those non-dimensional time. And remember, this is non-dimensional. We need to times the time scale, time characteristic time to get the retrieve the dimensional data. And the periodic time can be 2 pi divided by omega. Again, this TP hat is non-dimensional. Okay, so the dimensional form for the above parameters need to be multiplied by tau, and that's the characteristic time. Okay, so let's see an example. We have a passenger aircraft mass 20 tons and a wing area 50 meters square. It's flying at 240 meters per second at an altitude of sigma equals point out. Sigma is a density ratio, which means at a higher altitude, the air density becomes half of the sea level, and the sea level air density is 1.226 kilogram per meter cube is given. The coefficients for its longitudinal quadratic stability equations are B, C, D, E, and A is not given here because A is 1. And we can find B and C is far larger than D and E. Is that right? So this also confirms our assumption made earlier. So using no more than one iteration where appropriate, calculate the periodic time, the time to half amplitude, and the damping ratio of the phugoid and SPPO mode. Okay, so let's see. And we can follow the estimation procedure by plugging the numbers of B, C, D, E. A is there 1. Okay, and then we just do this first iteration. We can update the data on the right hand side once we have a new one, and then we can have the result from this first iteration. If you want to do further, you can carry on. I believe the data will be converged. Okay, so we have B prime, C prime, K1, K2 already now, and we can also verify K1, K2 is far smaller than B prime, C prime. So we have the coefficient for the quadratic equations, and we know B prime, C prime, K1, K2, and of course, so for now we can get the solution for each quadratic equations. Okay, and we know lambda is in the form of lambda plus minus I omega, and for SPPO we have lambda like this, and for phugoid we get two numbers for lambda, and they both are in the complex form. Okay, so we've solved the parameters for each quadratic equation, and for SPPO, if we solve its relative equations, we can have lambda equals minus 3.364 plus minus 5.027 times I, and then we can have the time to half amplitude and the period time. And for phugoid mode, we can do the similar things and get the value of lambda and then time to half amplitude and the period time. And remember, since we see there are little hats on top of each letters, and so it's a non-dimensional time, you need to times the characteristic time, which is 5.438 seconds. Okay, so this is what we have, and we just times this tau, you will have the TP and the T half. And for the short period pitching oscillation, we can see the period is estimated to be 6.8 seconds, but for phugoid mode, the period time is 206.7 seconds. So, and we can see the period is much larger. And for the phugoid mode, the time to half amplitude takes longer, much longer than the time to half amplitude as a SPPO mode, short period repeating oscillation. And so far, we can finish the longitudinal equations and how to, once the quadratic coefficients are given, and how do you get the properties of each of the SPPO mode or the Fugit mode. That's an objective for this class.